Okay, we're going to take a look now at how to conduct a paired samples t-test. This is not commonly used because most of the time you're doing an independent samples test, but there's lots of reasons why you could do a paired samples t-test. The classic over time, the pre-post is the primary one that gets thought of. But there's could be a similar, like two conditions on the same day within subjects. Like, do students recall more vocabulary words when tested with pictures versus when tested with tests only? The pairing is the same student with two different testings. Two scoring methods of the same work. This is what I'm going to do for my example today. Not this specific example, but this method. Is there a significant difference between rubric grade scales and AI-assisted grades? That's two ratings of the same artifact. This one's less common. Wouldn't be one I would recommend. To students receiving peer tutoring have a matched peer and how they outperform or underperform them. And look at this. Just want to point out, outperform, that's directional. So that would be a directional hypothesis on that one. Two instruments measuring the same construct to two different reading comprehension assessments produce similar mean scores, and that would mean they have to be on the same score. I'm going to be looking at some data, this science fair data, which is available in the Blackboard course. And what we're going to look at is we have these students. They're sorted in different ways. I've actually sorted them so all the test scores are together. So we have science fair projects, and they were judged by a rater, and they were given a score. So there's rater 1, which is in this column here, and rater 2 in this column here. And we want to know, did these judges rate in a statistically similar fashion? So we're going to grab the data. I'm only going to take the ones that have the paired information. I'm going to move it over to SPSS, put it in. Go to the variable view and just label them as judge rater 1, judge rater 2. Okay, great. So here's the data sitting in there ready to go. Typically, the first move you're going to make in any inferential analysis is we're going to do descriptive statistics first. Like I said, I like the frequency ones, so I'm going to put them both over. I'm going to pick the ones I want, which are the quartiles, the mean, standard deviation, min, max, and skew and kurtosis. I'm going to remember to uncheck the displaced frequencies and run it. Here we go. Let's just take a look and see what we've got going on here. We've got 61 samples, a mean of 81 versus mean of 83. A little different there. Deviation, 16, 11. They're a little off. Skew, we got a little bit over the tolerance of 1, so we want to be careful with that. And same with the kurtosis. So we'll look with caution at this data. Minimum of score is 25, maximum score is 100, and we're the percentiles on the quartiles, interquartile range flag. Okay, we'll come back here and now we're going to run the t-test. We're going to analyze, compare means, then we're going to come over here to paired samples, not independent, that'll be the next one. Pair samples t-test. We'll put judge rater in 1, variable 1, judge rater in variable 2. We'll leave everything else as is, and we'll let it run. Then we take a look. So we'll take a look at these results and look at the interpretation. So we had the means before, again, 81, 83. Are these statistically similar or are they statistically different? We got to find out. Okay, it does give you a correlation, and let's just say a word on. Does judge 1 and judge 2 correlate? And we can see there is statistical significance for this correlation. It's just a very high correlation. It's 0.88. It's almost, rounding, it's going to be 0.989, close to 0.9. This makes sense because judges are seeing good projects as good projects and poor projects as poor projects. So having high correlation is a good thing. The question is, though, if there's criteria, which there is in this study, are they judging the criteria the same way? So we can look at the paired samples results here. And what we see is we get some information here. We're not going to over worry about that. I mean, the mean is the difference between the two means. That's pretty straightforward with its standard deviation. We go and look at the t statistic. That's the calculation of the t statistics. It's negative 2.198. It would be positive if the data were put in the opposite order. That doesn't really matter. And then we have degrees of freedom, 60. Degrees of freedom are basically, the number of independent values in a data set that can vary. So it often takes into consideration how many IRMs are in the data sample. In this case, there were 61, and you take away 1 to ensure reliability. Anyway, we'll look at our significance. If you wanted a one-sided test, directional hypothesis in this case, it'd be 0.017. That's statistically significant because p is less than 0.05. I'm a two-tail guy. As you know, I don't believe in directional hypotheses, so I get 0.034. That is also statistically significant. So that means there's a statistically significant difference between the scoring of 80 and 83. These means over here, 80 or 83. You can tell that might happen because the standard deviation is different, so the curves don't look precisely the same. So you might be saying to yourself, well, wait a minute, you got a really high correlation. Why would they be different? And the difference has to do with where this data falls related to the means, not the correlation, which is point A to point B. So we're comparing means in this case, and this is where the means are different from one another, and in fact, in this case, they are. We then also want to look at effect size. Effect size is the practical application of the statistic. So we use the Cohen's d, which is listed here, and we have point estimate of negative 0.278. So that's a small Cohen's d. Small is 0.2 or greater, medium is 0.5 or greater, large is 0.8 or greater. So basically, when you have a small effect size, that means it really doesn't matter much. So even though there's statistical significance, in practicality, it's not going to matter so much in educational research. Now, there are certain situations where a small effect might matter. Look at the research that supports the work you're doing to make a determination. So we take this information from here, so from our descriptive statistics, and then also from our t-test, and notice we run the frequencies, and that comes out first, and then the t-test comes out second. The windows will just keep opening. And then we can write up our report on this. I've already done it for you. So we state the research question. In this case, I said, is there a statistical difference on the ratings of different judges on students' science fair projects? Period. Then we're going to state the hypothesis. There will be no statistically significant difference between judging scores on the student science fair projects. And the alternative hypothesis, there will be a statistically significant difference between judging scores on student science fair projects. Notice I don't put a direction on it. I just said there will be a difference. I don't see one's going to be better than the other. We set the criteria for rejecting the null, which is just p is less than or equal to 0.05. We compute the test statistic, and we get t equals 0.217 and p is 0.03. Remember, I'm pulling this data directly from the report. There's 217, 0.03. So just remember where I'm taking that information from here, goes into the template here. So we reject the null and we accept the alternative and we write that out. There was a statistically significant, p is less than 0.05, because remember it was 0.03, between the difference, and we report the test statistic, t, degrees of freedom 60, equals negative 0.217 between judge 1, mean, what the score was, 81.61, and judge 2, 83.04. Judge 2 scored the students higher. And we construct the confidence interval. We just pull that data right off of the table as well. From here, the confidence intervals. In parentheses, we put those. And then we report the effect size. And the effect size, again, was from the point estimate column, 0.278. That rounds to 0.28. Okay, and then we say it's a small effect size, so it has less practical application, even though there's statistical significance. And that is the way we test for a paired samples t-test. Next, we'll take a look at the independent samples t-test.